Hello everyone, my name is Shada Murshid and I am currently working as a research fellow at NTU Singapore. Today I am going to give a presentation on implementation of frequency adaptive damped SOGI based control for power quality improvement in wind solar PES based AC microgrids. A microgrid is defined as a group of interconnected loads and distributed energy sources within a clearly defined electrical boundaries which can operate under grid connected mode as well as islanded mode. The presented microgrid comprises of two renewable energy sources. First is the wind energy generation system and second is the solar photovoltaic generation system. A battery energy storage is utilized to support the presented system when grid is not available. A non-linear load is utilized which acts as a local load. Due to the presence of non-linear load, the grid current gets distorted. In order to mitigate this issue, a frequency adaptive damped second order generalized integrator is utilized for power quality improvement, which makes the grid current sinusoidal. The presented system comprises of three converters. These converters need to be controlled properly for proper operation of the presented system. This slide shows the control of the presented system. First is the control of generator side voltage source converter. For this, the reference generator speed is compared with the sense generator speed and the error is fed to the speed PI controller. The output of the speed PI controller is taken as the reference quarter axis current in inverse Sparks transform is utilized for transformation from DQ0 to ABC reference frame. The reference generator currents are compared with the sense generator currents and are fed to the hysteresis controller for the generation of switching pulses for the generator side voltage source converter. The control of DC link control voltage is done in two modes. First is the grid. When grid is available, the output of the DC link voltage controller is taken as the loss component. However, when grid is not available, the output of the DC link voltage controller is taken as the reference battery current. This reference battery current is compared with the sensed battery current and the error is fed to the hysteresis controller for generation of switching pulses for the bidirection converter. The control of grid side voltage source converter is shown over here. For this, first the load current as well as the grid voltage is filtered using the frequency adaptive damped second order generalized integrator. The structure of FA-DSOGI is shown over here. The output of the filtered grid voltage is shifted by 90 degrees to for the generation of quadrature component. The in-phase and quadrature component are summed vectorally to for the generation of the peak voltage. The ratio of the filtered in-phase voltage and the peak voltage is taken as the unit template. Feed-forward terms are utilized for accelerating the response of the presented system. The weight components are calculated as the ratio of the corresponding power and the terminal voltage. The summation of the weight components is taken as the net weight component. The net weight component is multiplied with the unit template for the generation of the net of the reference grid current. This reference grid current is compared with the sense grid current and is fed to the hysteresis controller for the generation of the switching pulses for the grid side voltage source converter. The steady state and dynamic performance is shown in this slide. Here we can see that the steady currents are found to be sinusoidal. An excellent tracking of MPBT is shown in this figure with a tracking efficiency of 99.8%. Here in figure C, we can see that the load currents are non-sinusoidal, still the grid currents are sinusoidal. This has been possible with the implementation of the FA-DSOGI based control structure. Here the battery charging is shown and here we can see that the grid current and voltages are in phase and the battery is charging. The dynamic performance under the change of wind speed is shown in figure A to B, where we can see that the reduction in wind speed has resulted in the reduction of the generator speed and generator power. The wind feed forward term has also reduced and therefore the net component has reduced and therefore the injection of power into the grid reduces. The performance under the reduction of solar insolation is shown in figure C2D. Here we can see that when the solar insolation reduces, the PV power reduces and therefore the PV feed forward term also reduces. This has resulted in the reduction of net component and therefore the power injection into the grid also reduces under this condition. The power quality performance is shown over here. Here we can see that the load current THD is 13.3%. Still the grid current THD is 2.4%, which is possible due to the implementation of FA-DSOGI structure. Moreover, we can also see that when both wind and solar are feeding the grid current THD is 3.2%, which is well within the IEEE standards. Following conclusions can be made from the above discussion. A satisfactory operation of wind solar BES based AC microgrid under various operating scenarios has been exhibited. Owing to the implementation of FA-DSOGI structure, experimental results under steady state and dynamic condition are found to be satisfactory. The presented system follows the IEEE 1547 and IEEE 519 standards and for a grid connected system, and therefore present a feasible solution for AC microgrid with non-near load and distributed energy sources. Thank you.